recording. So I'll try to admit a few more people, but other than that, we'll be starting. So welcome everyone. We saw there was quite a few countries from across the globe. So good afternoon, good morning, and good evening for those of you who are joining from various parts of the world. So today I'll be doing a lightning lesson. So it's a kind of it's a short lesson where I would like to share what I've learned over the years about forecasting metrics, right? So forecasting metrics are quite important, and I think it's kind of an area of forecasting that is not sufficiently covered. So without further ado, let's begin. So my name is Valeriy. I teach some courses on Maven, right? So I'm also writing a forecasting book that I'll mention towards the end of this talk. So as I mentioned, today we are going to talk about unlocking accurate forecasts with superior metrics. So that's the topic of our lesson. This is a forecasting proverb from my book that actually was something created by AI. So I'm trying to understand whether it makes sense or not, but it seems to be that makes some sense. And what it's trying to encapsulate is essentially, when we do forecasting, we are trying to measure something, right? As you're probably familiar, in order to get somewhere, right, we need to have some kind of measurement. If you're trying to drive somewhere, we need a map or sat-nav perhaps. And if you're doing forecasting, we need to kind of measure how good or bad our forecasting is. So in terms of forecasting metrics, just to kind of a few more ideas why they are important. So essentially, we need to take a step back and understand why we're doing a forecast in the first place, right? So usually we are doing forecast to make some kind of a decision, and that could be various decision depending upon the use case. So essentially, our kind of first consideration is absolutely critical is to make sure when we're creating or selecting some metric, this metric aligns with our business goals, right? And this is essentially what we're trying to do the first step. Perhaps as a second step, but quite often you see it sort of taking over, is we are trying to use these metrics to measure the accuracy, right? And make decisions, right? Again, I think this is like not sufficiently covered. The primary purpose, of course, of doing forecasting in the first place is making decisions. So we need to understand like what our decisions are, what are we trying to achieve, how we're going to kind of cover the quality of these decisions, and to align wherever is possible our metric with these decisions. So we are using metrics, of course, to also calculate and interpret forecasting errors. There are various metrics, of course, and we're going to talk about them, but one of the most important metrics, which is kind of also not getting sufficient attention in my experiences, is bias, right? So we need to make sure our forecasts are not kind of systematically over or understated. And in a nutshell, bias is absolutely critical. In any forecasting application, you would like to kind of get rid of bias as soon as possible. And essentially what it does, it's kind of calculating the average of actuals versus your forecast, right? Another reason we are kind of choosing metrics is that we would like to select a best model, if you like, right? Or a number of best models. And to do that, we need to have some kind of comparison, right? So in order to compare different models, and that could be based on certain horizons or perhaps for specific business units and so on and so forth, right? We need a good metric that can tell us for this particular application is one model is better than another. If you followed me on LinkedIn for a while, basically, you probably have seen me saying that forecasting is a game of relatives, right? There is no such thing as as good or bad result, which is absolute, good or bad. There is no such thing as, gold forecasting model or bronze or silver or anything like that. The results that you get are sort of dependent upon your use case, how hard is your data set, and what kind of decision you're trying to make, right? So it's all very relative. And again, just to recap, the results have to be measured based on what your decision case is. We'll talk a little bit about more advanced metrics today, so which is things are trying to capture uncertainty. These are sort of up-and-coming metrics we start to see more often being used by various companies, in particular CRPS as a recommended metric. And as I mentioned, metrics kind of help us to achieve multiple objectives, in particular selecting and evaluating the both models. So when I talk about metrics, and one of the reasons I'm doing this lightning talk, I think it's a subject which is first of all, it's absolutely key, right? And I think it's a quite underrated subject, if you like, because selecting metric is the first key point to success when you're building forecasting model or forecasting system. You need to kind of spend some time and invest some time to make sure you understand how different metrics work and, to align your metric with your use case. More importantly, perhaps, there are, like, as I mentioned, some metrics are better for specific use cases, but there is also kind of some general results where avoiding sort of metrics that are generically quite bad, and in particular MAPE, is perhaps one of the steps that you would like to take, right? And we'll talk about today why MAPE is not a great metric and what people try to do, and whether they succeeded or not. We're going to cover it today. So if you're interested in a kind of drop-in replacement, we'll talk a little bit about WAPE, which is sometimes you hear people refer to it as MAPE as well, but it's actually quite different. And we'll kind of talk a little bit about how and why it's different and why it sort of produces better results. I already mentioned uncertainty quantification. In a nutshell, when you see people are saying no forecasting model is correct, right? They're all wrong. That only applies to point forecasts. If you're developing probabilistic forecasting applications, somebody's trying to draw on the screen. So it was a mistake, but let's continue. When we talk about point forecasts, kind of always wrong, but in reality, you can actually produce a very good probabilistic forecast, which not only can be quite accurate, but also capturing uncertainty and providing you essentially with much more information to manage your inventory and so on and so forth. If you're talking about demand planning, or in finance, for example, it allows you to quantify risks and things like that. So I'm not gonna dwell about these two last topics, right? This is probably perhaps advanced topic and we don't have sufficient time to cover them, but that's something you can be aware about. When you're talking about aggregation and forecasting at different levels, you can also employ aggregated metrics. And temporal shape metrics, just to give you an idea, it's kind of more relevant to things like, for example, trading in finance, or if you're talking about like demand planning, there are things to do like with promotions and spikes and so on and so forth. So they're kind of capturing alignment in terms of shape. Generally, in demand forecasting, for example, is not that important, so we're not gonna dwell about those, but you can be aware there are certain things that you can do to capture those, right? Okay, wonderful. Right. So let's talk about a little bit about MAPE, which is perhaps the metric that a lot of people are familiar with, and it's quite simply, it's mean absolute percentage error. So what it does, it calculates percentage error based on a certain actual volume. And this metric is used quite a lot, right? Because it's very straightforward to explain. But in reality, when we look at it and we start to kind of go a little bit deep dive into this metric, we would immediately see there are quite a few issues with this metric, right? So we can see that metric is asymmetric, right? And it's asymmetric in kind of specific way, right? So it's actually disproportionately penalizes over forecasting. So it's kind of looking to promote forecasts as essentially kind of producing forecasts on the low side, right? And the reason for this is because we are dividing the error by the actuals. If you think about when actuals are quite small, this is kind of inflating MAPE. And in a way, it's becoming asymmetric. And as I mentioned, it's kind of stipulates forecast to go more on the low side. And if you think about it, if you have like very, very low volume, the metric can become very high, right? So it's kind of not very productive for our forecast because the metric can essentially go close to infinity. Another issue is that we cannot sort of aggregate this metric in a good way because if you're talking about various volumes, right? So you might have one product that has higher volume, right? If you have a business and it's kind of your product that is bringing you a lot of money, and it can have 10% MAPE, that's kind of should be more important to attend to than something that which is like very, very low in terms of sales, right? So MAPE doesn't take care of that, and that's kind of another issue with the metric. And as I mentioned, when we have very, very low values, it becomes kind of uninterpretable because it goes basically to infinity. So in particular, things like intermittent demand, right? When they're selling some units from time to time, and this is like very, very important pattern at a granular level for every company. MAPE is not a good metric. Right, so let's have a look. What do we mean by that, right? And it's if you look at it at the first time, right? We think about what does it actually mean for MAPE to be asymmetric, right? So quite simply, the kind of shape of the error of the MAPE metric is like that. Imagine you have actual value of 100, and then if you kind of over forecast and you go to 200, right? So you have 100 difference, and you divide by 100, so you get like 100%, right? So you see, if you kind of over forecast even more, then your error goes to essentially quite a large number. On the other side, you see that if you are under forecasting, right, your error is kind of limited, right? So if you think about it, there should be no particular reason why a metric should be asymmetric, and it's one of the things that doesn't help, right? So as I mentioned, there are quite a few issues, right? It's undefined at 0, where there is a lot of practical cases. It's asymmetric, it's boundless, so on and so forth, right? So there are some like studies that have shown if you do simulation and use MAPE, because of the way it's kind of handling the errors and it sort of promotes a low forecast, you can actually run out of stock in principal scenario, so which means you're gonna lose customers, right? So the general consensus is not to use MAPE nowadays, right? So there might be some other questions. How do we report it to stakeholders and so on and so forth? But one cardinal rule is never use it to evaluate the models, right? Because it's not a great metric. So what could be an alternative? An alternative could be WAPE, which is kind of wide version of volume related metric. And in a way, it addresses some issues with MAPE, right? In particular, because it only looks at a kind of volume sum. It doesn't penalize low volumes as significant as MAPE. It does take of the account of the high volume products or period of time. And that's a good thing, right? Because in the business, you want to kind of focus on things that are selling more. And if your model is not doing particularly well on this kind of high volume products or time, you might want to kind of tune it better there, right? Essentially, it has very easy interpretation. It's also like percentage error of you know, error, predicted error, predicted volume or forecasted volume versus actual volume, and it sort of gives very clear meaning to stakeholders usually, so it's quite easily to explain. The metric doesn't disproportionately penalize under forecasting, which kind of reduces bias that we saw maybe has when it's under predicting, right? So I mean, I written here, it has a drawback if you have, of course, very kind of low volume product in general, then of course your total volume is also quite low, so it might be becoming bigger, but is not as critical as with MAPE. Right. So let's have a look why this happens. So if you look at the formula, this is the formula for MAPE. And essentially what it does, it kind of sums individual percentages of errors, whether it's over horizon or various products. So you see individual percentages are summed up together without kind of taking into consideration of the volume. Weighted absolute percentage error, on the other side, you see the formula looks very, very similar, but in reality, you're basically summing up both numerator and denominator. So you kind of no longer summing percentages, you're summing absolute values. And by doing that, it sort of focuses on the volume of particular products, for example, or particular horizon of time. This is how it looks like. So, you know, if we did a comparison and we did a plot of these two different situations, we could see that actually WAPE is kind of taking contribution of volume. And in this case, it's not inflating error because, you know, in this case, it might be some very small volumes, but it's kind of putting things on the same scale. And we are kind of good. So the first learning, I would say, you know, as I mentioned, do not use MAPE unless you absolutely have to, and only report it as a kind of last stage, but never use it for evaluating, comparing models and so on and so forth. And if you really need to kind of report some kind of metric which is similar to MAPE, try to kind of just do this flip switch, because it's kind of has the same shape in terms of percentages. It's very easily understood to stakeholders, but by doing this kind of substitution, you are avoiding all sorts of problems that we spoke about in terms of MAPE. Right. So let's talk about another metric that you might have seen, and this is quite interesting. So it's called symmetric mean absolute percentage error, and this is how it's defined. So you see the difference that they made was actually in the denominator. So instead of just having actual values, they kind of took the average between forecast and actual value. And the idea that was that by doing that, we kind of were hoping that it would become symmetric. The problem is we actually didn't solve this sort of asymmetric nature of MAPE. We introduced another issue. And whilst, as I mentioned, MAPE was kind of encouraging under forecasting, this one is actually can be shown. It goes in the opposite direction, so it's kind of encouraging over forecast. All right. So the way to see it, and usually it's kind of, you know, if you haven't been dealing with these metrics for some time, you're usually kind of thinking about how do I actually determine what to do, and to compare, like, you know, over and under forecasting. You essentially all you need to do is freeze the actual, because the actual is something that is going to happen, whether you're going to under forecast or over forecast, and then you just look at two situations. One is kind of over, another one is under. And if you do the plot of this SMAPE, you see it's clearly asymmetric, and it's kind of penalizes under-forecasting. So it's kind of goes in the opposite direction now, encourages over-forecasting, right? So not a great situation, right? So it's kind of also doesn't work, right? So what do we do? Then people started to say, okay, in addition to the issues that we face, we also have somehow to kind of aggregate errors over either time periods or like various products, right? If you have like different products, the same percentage error is going to translate to higher absolute error on a kind of larger selling volumes compared to lower selling volumes. And people said, okay, why don't we kind of normalize the metrics in some shape or form? And essentially, if we looked at the product errors for these two products in orange and also red, if you kind of normalize it, then kind of become on one scale, right? And after they become on one scale, we can do various things with them. We can do hopefully aggregate them and so on and so forth, right? So this is like quite a good, very straightforward and powerful idea. And the question is like, how do we do that, right? So for example, one of the ways people started to normalize these errors was by using mean absolute scaled error. So that was a metric proposed by Rob Hinman back in 2005. And this is kind of the sort of metric that usually you will see people who are at intermediate level forecasting would start to use, because they are kind of already aware of the limitations of MAPE. And then they say, okay, let's just use MASE. And Rob Hinman, he created this thing. And what it does essentially, it does what it says on the It kind of normalizes the error. It computes the absolute error, where the error, in this case, it's all like forecasting horizon, and then it basically divides it by the error of a benchmark, right? So we'll see some benchmark in this talk today, and benchmarks are quite important. Normally, benchmarks are either some kind of business rule that is already there that people use for forecasting. For example, in retail, quite often you'll see you'll have seasonality, right? And in retail, sometimes you have seasonal sales from last year, and you just take sales on the same day from last year, and it's usually quite a good metric, right? So you can use this kind of benchmark. In this case, it's kind of not specific to retail or industry. And what he said, it's actually, let's just take naive forecast. A naive forecast, essentially, if you're predicting something for tomorrow, you just take a value of this variable today. And essentially, this is what Hinman proposed. So it tends to work quite well generally, but it sort of creates additional issues, right? And the issues are coming from this sort of innovation. For example, if you think about it, if you have like something, we are predicting something which is rapidly oscillating, right? Or something, moving very fast, you are taking the previous value. So imagine if you're predicting here, you take this value, but then it kind of goes down the next day, and you already predicted with a high value. So your forecast in such situations will be, your forecast will be quite wrong. And that in itself is not a problem, but the problem is that because the error of naive forecast is higher, you kind of get a lower value of MASE, and that's not coming from your model. That's coming from the fact that the baseline forecast is not great. So that's just something to be aware about. And a general advice, is not to kind of discard MASE, but you can use it, but only, don't use it in isolation. Always use it with some other metrics, right? Now let's talk a little bit about standard metrics that you probably saw. One of them is root mean squared error. It's quite simple metric. It's just a sort of square root of the deviation, and it's quite often used. It's very popular. This is, of course, not scale independent, right? So you have to do some extra kind of steps to make it scale independent. but generally it's quite well-used metric. So you would see RMSE and also MAPE, which is just basically absolute value. I'm not covering it as well, but you will see people use this kind of metrics to evaluate forecasting models. But again, they are not scale independent, right? So you have to be kind of careful when you do this evaluation that you're not comparing them across series, which might have different scales. So one of the things that it has, it's very sensitive to outliers, right? Which could be a good or bad thing. So you have to think about it, what it matters in your scenario, right? Do you want to remove the outliers, or do you want to keep them? And in that case, you'll probably need to do something, because on these outliers, your metric will be quite high. And another good quality that it has, it's actually, if you think about it, squared error of this kind is minimized by the mean, right? So unlike absolute value, which is minimized by the median, this is minimized by the mean, and this is actually quite attractive, because if you are dealing, for example, with intermittent demand, then you would not want to predict with the median, because median will be basically zero, right? Such forecast would not be useful. But in such cases, RMSE is kind of okay. So what do we do to make it scale independent? Well, we might do the same kind of trick as we saw in the case of MASE. We can use sort of benchmark, which is naive forecast in the denominator, and then it's becoming quite interesting, right? So if you kind of created a model which has lower error than your naive forecast, for example, you are essentially outperforming naive benchmark, which is like what you're trying to do. As I mentioned, the kind of forecasting is a game of relatives, right? So you should not be trying to achieve something absolute, but you should just try to get better forecasting process in place, and usually use a comparator with naive or some kind of business benchmark, right? Again, the same issue as in MASE case. If you have something rapidly escalating, then it's not been handled well by naive forecasts. So you might want to kind of think about different benchmark. For example, if you have retail and your sales are quite seasonal, instead of kind of having naive forecast, you take a seasonal naive, which is T minus 365, right? And that tends to work quite well. So forecast value added, right? What is this concept? It's actually quite important concept. I mentioned that forecasting is a game of relatives, right? So we kind of comparing models to each other, methods to each other. And what you're trying to achieve is improve forecast. And forecast value added is a framework which allows you in a structured and disciplined manner, if you like, to improve the process, right? So the concept is very simple. It's kind of just looking at some kind of relative values of the models. You can look at, if you're using, for example, MAE, which is absolute value of the model, you just divide it by absolute value of the error of your benchmark, and then you just basically compute this one, right? So it's becoming scaled, right? 0 to 100%. So forecast value added becomes positive if your model is outperforming baseline, and negative which is when it's underperforming, right? So the idea is to kind of add value, if you like, right? And if you think about it, how forecasts are usually done in companies, usually a large company would have some kind of demand planning software. So the first step would be to compare how this software does compared to some kind of naive benchmark, depending upon the industry where it is. And then you'll see demand planners will do some kind of manual adjustments. And again, you can use this to evaluate whether demand planners are adding or destroying value compared to your demand planning system, right? So you can kind of look at various steps in the process when your forecast is getting transformed, right? And the idea is that every step is kind of adding value, right? If, for example, some of your demand planners are not adding value, they perhaps should not deal with particular skews. Maybe they're quite already well predicted, so they're not adding value. They should do something else where they can actually add value. So this is how we can use forecast value with RMSE, right? And this is actually something that I created and I used. So it's kind of a little bit of a trick, which is powerful in a way, not only because it does things correctly in terms of your model evaluation, but you can actually communicate it to your stakeholders, right? So we have a case which is suitable for root mean squared error, and you have a good benchmark. You can kind of do these computations, and then you can demonstrate to your stakeholders that your model is actually kind of adding value, and you can quantify exactly how much value is being added. So let's have a look at forecast value added, just to kind of summarize how we can use it in various industries. We can use statistical forecasts that are produced by demand planning solution or human planners, and compare it to perhaps naive benchmarks like seasonal naive or naive at skew or store level. In finance, usually you'll see sometimes people on social media, they would kind of post some complex solution, and they say, okay, actually we kind of created a model that brings profit. And when you start to actually deep dive and check whether this solution is doing better than random walk, and random walk is basically naive forecast, it's not kind of actually outperforming forecast. So as I said, it's a game of relatives forecasting. So in that case, all the people have done are basically spend a lot of time and money by training some sophisticated models which do not bring any profits, right? And this is quite standard. This was not only on social media. You know, we saw some papers, in particular transformers. There was a famous case where a new transformer at the time was published called Informa, and also even got some kind of top paper at the top paper award at the conference. When people actually looked at it, it claimed it was predicting exchange rates 2 years ahead. It was actually not outperforming random walk, right? So in energy, what you would do usually is you would look at historical patterns, right? So energy consumption and prices, they tend to be quite seasonal. So there is clear seasonality over time of the year, day of the week, and time of the day. So you would kind of try to create some benchmark and also use forecast value added framework to see whether your model is adding value. What is good about forecast value adding? You can actually demonstrate systematically which parts of your forecasting flow create value and which ones are not. So you can actually kind of not do adjustments. For example, human adjustments is quite scalable, right? And you can do all sorts of comparisons between, for example, demand planners, and compare demand planners with demand planning solution or solution of your data science team, right? So the kind of possibilities are quite boundless. It's quite a popular framework. It's been around for a while. But as I mentioned, you have to think about what your baseline is, right? So we saw that when there is oscillating kind of patterns, naive forecasts are not good. So the first thing you would do is kind of understand your company's business and select the proper baseline. Aggregation matters, right? So in terms of both metrics and also things like RMSE that I mentioned, for example, here, this one, it's a good kind of practice to aggregate over time, is not to add them using arithmetic mean, but actually using geometric average, which, if you think about it, is basically kind of doesn't produce bias over time, right? And if you kind of divide these fractions 1/2, then 2/3, it collapses to 1/3, right? So it's actually a very, very good thing to have in mind when you're doing averaging across time. So when you have some kind of products, for example, a dashboard or a system, usually it's sort of makes sense to report these different stages of FEA. Like model A would produce 12.5% versus naive, which is good. And model B would produce 4.3 versus human, right? So in that case, what you might say is actually model is doing better than human, so perhaps human can do something else where they're better at. So it's a very good framework. So let's talk a little bit about probabilistic forecasting and what kind of metrics you would use. So if you did some work with probabilistic forecasting, then you would see some things like quantile loss. Essentially, it's comparing the values with quantiles, and it looks a bit like that, right? But perhaps easier is to see it's like that. So we see it's kind of just like an angle, and you would select this parameter tau, which is done on the basis of what's more important for you, whether to penalize like over forecasting or under forecasting more. This is quite a natural kind of metric, probabilistic metric, and it's essentially when you select tau of 0.5, it reduces to your median, right? So it's kind of situations where you have MAE as a good metric. You can just use this to predict median. It also has some applications. So, for example, if you're interested in the sort of service levels, right? 80% service level being in stock to be able to service your customers, you probably can select something like that. Yeah. It has good qualities, so it's a proper scoring rule. Essentially, what proper scoring rules are the kind of metrics that incentivize models of forecasting to report the true beliefs, right? So they're not able to kind of cheat or report something else. So they kind of have some good qualities and incentivize people or models to report whatever probabilities they kind of produce. And you see it sometimes also being used. I mean, I've seen it used by companies also in forecasting competitions. Its quantile loss is quite flexible, right? So you can create a very sophisticated model. For example, deep learning model, just train it on quantile loss and you are good to go, right? So key benefit is especially like good in capturing uncertainty and skewed distributions, as I mentioned. Parameter tau controls it, like, where you want to be. Do you want to penalize or forecasting or under forecasting, and you can select appropriate shape. So let's talk a little bit about something else. And this is another metric for probabilistic forecasting. It's called Winkler score. All right, it was created by a guy called Winkler. I think he was in weather forecasting. And essentially, it evaluates the quality of your prediction intervals subject to confidence level, right? For example, confidence level simply means we want to be 90% confident that our forecasts fall within this interval, which is like low to upper bound. And we calculate Winkler score by basically account for these two things, right? Whether it's kind of falls inside the interval, and if it's like inside the interval, that's good, right? But we also don't want to have very kind of wide intervals, right? So if the intervals are quite wide, we kind of penalize for that, right? So it's essentially what it is. This is a formula. So if it's like actual values inside the interval, simply is the width of the interval. And if it's outside, we do this kind of penalization. We compute, if it's like lower than lower bound, we compute this one. Or if it's upper than upper bound, we compute this one. So it's a very kind of, good metric, very intuitive. It's kind of computing the right things, if you like, right? Because we want to forecast to be inside the interval, and also interval to be narrow. And this also happens to be a discrete kind of approximation to continuous rank probability score, which is we're going to talk in a minute. But before that, we are just going to do illustration, because if you see it the first time, it might be, tricky to think what we actually do. So in this case, imagine our model produced an interval from 8 to 12. And we have two forecasts. One is in green and one is in red. So in this case, quite simply, because it's already inside the interval, we don't penalize for it to be outside. It's just simply the width of the interval, which is 4, right? So this would be 4 in this case. When it's red, we do two things, right? We add to this 4, which is the width of the interval. We do this. We add to this kind of penalization. So it's distance between this dot and the next closest bound, which is 1, and we divide it by 0.2, which is error corresponding to 80% confidence. And we basically get these numbers, right? So it's in this case, it's 13 So just to recap, it encourages more narrow intervals, and also it's trying to make sure the model is calibrated, right? So with 80% confidence, we expect 80% of the points being inside. So let's talk a bit about CRPS. So CRPS is kind of the preferred metric in probabilistic forecasting. It has some very good properties. It's a proper scoring rule. So essentially, what happens in probabilistic forecasting, if you kind of go beyond intervals, you'll produce the whole probability curve, right? If you study statistics of probability, this is cumulative probability distribution curve. This is like what your model would produce. And then you think, how do I actually evaluate it, right? So the way to evaluate this is actually quite simple. So forget about this, it's like a MASE formula. There is a very easy way to interpret it. Imagine we produced this forecast, right? So the median forecast would be, in this case, around 10. And then we have some probability that it can be higher or lower. And then we have observed value, which is around 12, right? So we are interested in a couple of things here. So one is basically the distance between the actual and the median. So if it's like larger, then our forecasts are a bit biased, but also in the ideal case, because we already know the value, it's 12. So in probability, it means that anything below 12 is not possible, anything above 12 is not possible. So it's a step function, right? Probability goes from 0 to 1. And this is what our model produced. So we basically just compute this, difference between these two in orange, we square it, and basically sum it all up across this whole area. And this is how you calculate CRPS. So essentially, as I mentioned, Winkler score is kind of approximation to it. If you do it at various confidence levels, you get CRPS. CRPS does it like for all confidence levels, and essentially what you would like to have is the red one is becoming like this step blue, right? So you get the point forecast in the right place, and you have very, very kind of narrow interval around that. So I think this is just almost there. So just to kind of explain a little bit more, why do we want to do probabilistic forecasting and use CRPS? Well, as I mentioned, point forecasts are always wrong, right? So by producing probabilistic forecast, if you achieve multiple objectives. You create an interval of uncertainty. And in inventory planning, for example, you might want to know what is going to be sort of high demand and what is going to be the probability of high demand. So you need to kind of account for it and perhaps have some inventory to satisfy client demand. Likewise, on the lower side, right, you can also kind of manage your inventory and risk. In finance, you can manage risk. If you're doing trading, you're interested in like where your returns, for example, are going to be, and what the probabilities are going to be lower than certain value, and so on and so forth. So here is an illustration. We have two models that are producing the same point forecast, right? So they're exactly the same, 10. But by only looking at point forecast, we're essentially missing quite a lot of information, because in this case, the model which is in red is overconfident. So it's kind of saying, I'm very confident the values are going to be around 10. In reality, it's going to be more like 6 to 14, right? So this model is actually better from probabilistic perspective, because both of them have the point forecast correct. Like here, it would be here, but one is kind of producing intervals which are not great. The other one is actually accounting for uncertainty and risk correctly. So that's essentially it. If you are interested in learning more, I have a course on maven.com, which is this lighting lesson is connected to, right? Because Maven is kind of running these courses for various selected courses. I have a book as well, which is currently on early release, right? So there's several chapters that were published already, and the rest is going to be published in 25. So if you're interested to deep dive, you're more than welcome. So let me stop the recording, and we probably have a couple of